Okay. So in that last problem you worked on, it said that the velocity of this falling steel ball was negative 32t. So if we just graph that velocity function, it looks something like this. Okay, so why negative? Because, so that would indicate that the direction of positive displacement would be up. So therefore, if it's falling down, its velocity is negative. Okay, so you get something like this. And it was a very open-ended question. It's, it just said, create an accumulation function based on an approximating step function. So I didn't tell you what the interval size was, and I didn't tell you to use right or left or mid if you want to use mid. So that's kind of up to you. So here's how I did it. I used, well, you tell me. What interval did I use, and what scheme did I use to build this step function? 0.5 second intervals, and is this left or right? This is left because I'm basing the rate of change in a given interval on the actual rate of change on the left side of the interval. Okay? So don't look at the way the flags are flying. Okay, it's where we're picking the actual rate with respect to that interval. We're picking the actual rate from the left side to be the rate for the whole interval. Okay, so if I do 0.5, here's what I get for the step function. Constant rates, 0, negative 16, negative 32, negative 48, negative 64, negative 80. What's this? Feet per second. Okay, feet per second. So the whole point of doing the tax function and the rocket basketball was because if we have a function like this, we can build the accumulation function. We can calculate amounts of accumulation based on constant rate, and then we can build an accumulation function. Okay, so we can't do that with the actual rate function, where it's just always changing, right? So the rate is always changing. So the reason that we did all that stuff with taxes and rocket basketball was, if we're given a changing rate function, we're going to start by creating a step function, like the tax function, like the tax rate function, or like the rocket basketball. Okay? And then from that, we can get little bits of accumulation. So how much will the height change in the first half second according to my approximating velocity function? How much will the height change? 0, because it's, according to my approximating function, the speed is 0 for the whole first half second. All right? So 0 is the rate times a change of x, 0.5. Okay, and so, but now getting into the second half and third half seconds, we can calculate these little amounts of change by what? Rate times delta x. Rate times delta x each time. And so here I'm showing the resulting, these are changes in height in each half second according to our approximating rate function. And then as that happens, then we get a approximating height function that looks like that. So here's one representation of that height function as a graph. Another representation is as a table. We did this. And you did this on your quiz. Okay? So at x equals 0, the height is 120. What is it a half second later? What's the height? Still 120, because in that first half second, according to our function, the height didn't change. So now in the next half second, if 1 second, what will the height be? How much will it go down according to our rate function? It'll go down 8, so the new height will be 112. Okay? So this is based on our delta h's. This value, we get the next value of the height by just adding little changes in height. Remember this principle. Old value or new value of y equals the old y plus the change in y, right? Old value or new value of y equals the old y plus the change in y. So I can build a table just by applying the change each time. So according to our approximate rate function, it'll hit the ground in exactly 3 seconds. Yeah?
In the piecewise function on the left,
yeah.
Can you explain why the function that follows the previous function also includes?
No, it shouldn't. That's I don't know. I did that in a past life, I guess. I don't know. These should be less than, strictly. Yep, thank you for pointing that out.
Yeah, you can't have it. You can't have a number go to both lines. Okay, is that consistent with what we did before? Okay, thank you for pointing that out.
Yeah, you can't, if x is 1, we can only indicate one line in the function, not two lines, okay? So in this case, it would be the second line. If x equals 1 second, the rate is negative 16.
Okay, and so, but we also,
We still had another representation. So we have this representation of the height function, a graph. We have a table, but we also built a
piecewise linear function out of step. We did that lots.
So there's that. That's old hat. We know how to do that, right? Given those constant rates, we know how to use that point slope form to build up the piecewise linear function. Okay, and then so these points just end up being the corner points of that, right? The ending points of each segment is what these points are. They're just the end points of each of those segments.
Okay, so this is
a kind of a full solution to that problem number 7. What you turn in on Wednesday, so you've got, so I'm just going to ask you to do it different than this. So do it any way you want except for right or left with 0.5 second increments. So just all you have to do is change the increment time, or if you want to do 0.5 second increments, you could do mid. You could base it on the midpoints of each interval. Okay? So just don't turn in on, when you turn in Wednesday, don't do 0.5 with left or delta x equals 0.5 with right. Anything else is fair. Okay. What if we've got 2 extra days. What's that?
So to define it at the mid, would you just take like 0.25 and use that value?
Okay, so mid.
we haven't talked about mid. It's basically you're just in the point. So how would we find the mid?
Would it just be halfway between the intervals?
Yeah, so you're going to take the x value at the midpoint and pick off the rate there. Okay, so that would end up looking something like this if you use mid. Your steps are going to look like this then. Okay? All right, so today, but what if there were 20 or 100 steps? What if there were 20 or 100 steps?
What would this step or this h be like? Say there were 100 steps, then what would step and h be like? Yeah, we'd have 100 lines in each, right? We'd have 100 lines in our step function and 100 lines in our h function. Okay? I'm not that cruel. Okay? So what we're going to work on today is we're going to define step as a one-line rule. Instead of having it in a bunch of lines, we want to define step so that in one line, it gets us the correct constant rate of change given the value of x. So the input is x, the output is whatever constant rate of change according to the scheme that we've defined. And then our next goal in the next couple days, this is our real goal, is to get the accumulation function as a one-liner. Okay? And I actually showed that to you about a month ago or 3 weeks ago. I showed you that. Okay? So to scare you. Okay, but anyway, but you won't be scared once we build it, right? Because we're gonna piece by piece we're gonna understand it. Okay, so that's our next goal, is to write the accumulation function as one line instead of piecewise linear. Okay, so let's review. So writing this step in one line goes back to what we did on Friday. So you should be able to see in gray there the rate function, which I'm calling R. So here's a series of questions. I want you to take a couple minutes to answer. Okay? So talk to the person next to you. Let's see, maybe just 2 minutes. Talk through these questions. See if just to refresh what we talked about at the end of class Friday. Okay? Go. Okay, what do all the small red dots on the x-axis represent? So all this whole line of dots, why are they there? Just to mark off the intervals, right? We have a constant delta x, and that those red dots are showing the endpoints of the intervals according to that delta x that we picked. Okay, what's meant by the current x value? What is meant by the current x value? Where do we see that here? Yeah, so the current x value is, we think of x starting at our initial value a. I think in this case it's negative 1.4, and then we think of x increasing. And so if we pause, whatever the value of x is, and that's what I'm showing by this blue bar for the x. So then what's the current interval? The interval that the current value of x is in. Okay? So right now I'm showing the current value of x as, can you read that? No, it's actually right on 10. So you see it's straddling the 1 and the 0. It's right on 10, okay? So yeah, 9.9, 10, something like that. So the current value of x is about 10. And the current interval then is referring to, yeah, so the left side of it's where the hand's pointing, and the right side of it's this little dot here. So that's the current interval right there. Current value of x is about 10. Okay, so what does that larger red dot where the finger is pointing, what does that represent? Why is that significant? Start of the interval. Left-hand point of the interval. Yeah, so it's the x value at the left side or the starting side of the current interval. I'll say that again. It's the x value at the left side of the current interval. And why is that important for us? Why are we interested, given a current value of x, in identifying what that x value is at the left side of the current interval? Do you remember why that's important? Yes, sir?
We're adopting, like, whatever the rate of change is at that x, we're, like, taking it for a span of an interval.
Yeah, did you ever say, so whatever the rate of change is at that x, that's going to be the whole rate of change for that interval in our approximating step function, right? And you can see that up there, the blue, it's being formed right now, right, in that current interval. That step is being formed right now based on the rate at the left side of the current interval. Okay, so let's do an example here. So in this animation, a is negative 1.4, delta x is 0.37. Suppose the current value of x is 10, that's what I'm showing. We want to figure out what is the value of the left side. So what I don't want you to do is just look in your notes at the formula that we came up with on Friday. I want to kind of do it again, just to think through it again. So can you come up with reasoning from scratch, without using the formula from last time? Can you get that value that the finger is pointing at, the left side of the current interval? Take 30 seconds or a minute, see what you can do. Can you get that value without a formula?
Okay. So, I'm just gonna, here we go.
So what we need to do is we need the hard thing about this was counting up how many whole intervals starting at our value of A up until X. The rest of it's kind of easy, but the hard part was how do we get that distance starting at, or the number of intervals starting at A, in this case negative 1.4, and ending at 10. How many intervals are in there? Okay, you might be able to count that if you could keep your wits about you, but you know that I can make the intervals half as small, and then you wouldn't be able to count it, and that's,
So we need a mathematical way to count. So we want to start by getting this distance from A to the current value of X. So what is that distance as a span of X values? X minus A. Okay? So
X minus A, final value minus initial, right? Final minus initial gives you that change, that big change.
So how are we going to get how many intervals are in there? We're going to take that X minus A and divide by, or measure it in. We want to measure it in the terms of a unit of the width of each interval.
So it's right, we're measuring the top in the units of the denominator.
So let's do that. What is our X is 10, right? A is, and this is, and that will give us the number of intervals, including a partial interval at the end.
Does that make sense?
Does anyone calculate that? 30.8.
Yeah.
So the 0.8 then is this right there. That's the 0.8, which we don't care about, right? If we're interested in that, then we just want to lop off the 0.8. And how do we do that? So we have this device called the floor function. If we take the floor of that, which is symbolized this way, that takes that 30.8 and says, I'm going to give you the highest integer that's less than that, the highest whole value that's less than that, and that's exactly what we want. So that becomes 30. So now there are exactly 30 intervals between them, and so we should be home free from here. We got the negative. What are we going to do? How are we going to get that X value? Well, it's going to be 30 times, how wide is each interval? 0.37. But it's like we're shifted back 1.4, right? So we're going to add A to that, add negative 1.4. And that should give us the,
Starting at negative 1.4, add 30 intervals of width 0.37. Does it make sense?
and we should get something like 9.7 or something. What do we get?
9.7.
Exactly?
Yes.
And that looks about right. If we see where 9 is and where 10 is, we're closer to 10 than 9. Okay, does that kind of make sense?
So then our formula is, it's going to be this, our full number of intervals is x minus a over delta x. And we're going to multiply that full number of intervals by the width of each interval and add that to a.
And that, what does that give us? That gives us the x value at the left side of the current out interval where x is, where that x is.
And so we said we can make that a function, and we'll call that function, we'll name it left. So that whole thing together is the name of the function. Our input is the current value of x. And what is the output? Is the output rate? And that's modern accumulation. It's an x value. It's another x value. In this left function, you put in an x value, you get out another x value. Which one? The one at the left side of the current interval. That's key, because as things get more complicated, students often fall into the trap of thinking that left gives you a rate or gives you an accumulation. No, it gives you another x value. Specifically the one At the left side of the current interval. Okay. Questions on that? So then in your reading, it kind of goes through that all again. You do answer some questions in your reading. Okay, important stuff. So let's. What was our goal today? Our goal was to write step in one line. Well, we've got all the tools to do it. So here we go. Write step in one line. We're very close. Okay, so here is that same thing again. Just zoomed in a little bit. And down here, I'm showing the current x values in a table form here, written out by 0.1, from all the way from 0 to 1.7. Okay, so these are all these current, thinking of them as values of x from 0 up to right there, 1.7. So, given that this function we're building a step function based on the changing rate function r, what I want to know is, say, right here at 1.2, how can I represent what is step of 1.2? How can I represent what step of 1.2 is? So let me just pause it right there at 1.2. Something like right there. Oh, I had it. Go back. So here's the current value of x, 1.2. Current value of x of 1.2. How can we represent what step of 1.2 is if we're basing our step function off of this changing rate function r? See if you can do it. See if you can do it. Talk to the person next to you. What can I write in this box right here for step of 1.2? Go. Did you get it? How many people got it before I put it up there? Oh no. How many people got it before I put it up? You got R of 1. R of 1. Not enough. Okay. Why is it R of 1? We want at 1.2, this value of the step rate is going to be the value of the rate at the left side of the interval. And how do we represent that? R of 1. Okay. So what is step of 0.3? Step of 0.3. Oh, it's so easy now, right? And what's step of 0.6? Does this make sense? This is just now the symbolic way to do the same thing we've been drawing like for the last half week, right? We've been drawing these bars. Symbolically, what are they? Well, it's the rate at the left side of the interval. It's the rate at the left side of the interval. Okay, what about 1.7? R of 1.5. So this is our step function. Based on the original rate function, so you see a constant rate for 0 to 0.5. That constant rate is the same as the rate at the left side of the interval. Then it jumps. That constant rate is the same as the rate at the left side of the interval, or at x equals 0.5. And the next interval starts at 1, so all those rates will be R of 1. Does it make sense? Okay, but there's a middleman, right? So here at 1.2, we've got x of 1.2, but we're putting 1 into R. So what's the middleman? 1.2 first has to be, you could think of, transformed or mapped to what value first? 1. We want to map, do this red. Don't we want to map 1? Don't touch on that. Okay, so don't we want to map x equals 1.2 to 1 so that we can plug 1 into R, right? So what does 0.1 get mapped to? 0. So we can plug 0 into R. And then what does 1.6 get mapped to? 1.5. So this is our middleman. Our middleman is the x value that we're going to plug into R. So we've got the original current x value. We've got the x mapping to the x we're going to plug into R, and then we plug that into R. And so that will give us step of the original current value of x. So what is this mapping from x to these red values? What is that? Should be familiar. What function is that? It takes the current value of x and it maps it to the x value at the left side of the interval. It's not floor. It uses floor. It's left. That's exactly what left is. It's exactly the one we just worked on and built on Friday. So we're ready to write what step is. Here we go. Step. What is step x? What do you do in order to get this value given the current value of x? Take the current value of x and we do what with it? Put it into left. And then we take what's in left and we put it into right. So can you write the rule for this? You take the current value of x, you get what left would give you. And then you take that and you get what right would give you. Who can write the rule? See if you can write the rule for step x. What is it? So we start with the current value of x and we put it into left first. And then we take that and we do what? We put that into, look, one line version of step. One line version. Take the current value of x, put it into left. Take the value of left, put it into the right. It tells you, it gives you that step function. Anybody have a question? Okay, hold on. Hold on a sec. Hold on. Hold on. Any questions? All right. So let's, here's what a card should look like or not look like, okay? So, you're right, I learned that. Don't just write a formula. I learned